All right. So we have seen how to solve a linear congruence and when such a congruence is solvable. Next, we are going to consider a system of linear congruences where there can be any finite number of congruences like this. A1x congruent to B1 mod M1, A2x congruent to B2 mod M2, and so on, and we finally have ARX congruent to BR mod MR, where of course we have the usual conditions on these parameters, the AIs, BIs and MIs, and the conditions are that these are of course all integers and these moduli are positive integers. Moreover, because we do not want to have a degenerate congruence, the AIs are not divisible by the corresponding MIs, so that the left hand sides do not become 0. Okay. Become 0 means they do not become congruent to 0 mod Mi. Additionally, we are going to consider something else. We assume that the moduli Mk are pairwise relatively prime. What that means is simply this: the greatest common divisor of Mi and Mj is equal to 1 for distinct I and j. Right. And I and j of course lie in this range. They both lie between 1 and r inclusive. Alright, now if we want to find a simultaneous solution to all these congruences, say those integers x we are seeking that will satisfy all the congruences simultaneously. Just like you have a system of linear equations, a system of differential equations, just like that we have a system of congruences. Then obviously we would want all the congruences to first of all be solvable, because otherwise obviously there won't be a simultaneous solution if say one of the congruences, say the first one, is not solvable at all. So that is why we next write these things in order to have a simultaneous solution to the above congruences. They must all be solvable. We also assume that they are solvable. And now we know precisely when each such congruence is solvable, because we have already seen the theory of a single linear congruence. And the condition for solvability is that the GCD of the coefficient and the modulus divides this number, this integer b. That dk divides bk for all these k's. Where dk is of course the GCD of ak and nk. Okay. Now in this situation we can, with these additional conditions, we can simplify these congruences. How? By dividing each congruence, the kth congruence, by dk. And when I say that, I specifically mean dividing not just ak and bk, but the modulus mk as well by a previous result. Okay, you recall that. So doing that, we are going to get another system where the equations will be simpler. Let me just keep this system and right below it the other system. If we do so, if we divide each equation by its corresponding dk, we thus get the following system, where we denote the coefficients, because these are going to be new, b1 prime mod n1, a2 prime x is congruent to b2 prime mod n2, like that. And finally we have ar prime x congruent to br prime mod n r. Now we will write what these new quantities are. They are all the old quantities, corresponding old quantities divided by the corresponding GCD d. Where ak prime is ak divided by dk, bk prime is bk divided by dk, and nk is mk divided by dk. For all our possible case. Not that it makes sense also. Already, because dk is the GCD of ak and mk, so dk already divides ak and mk, and that's how we are getting these integers ak prime and nk. But with that we also have the condition that dk divides bk, and in fact that is why the kth congruence will be solvable, so that bk prime is also an integer, and that's why you now have this new system. Moreover, the condition that the mk's are pairwise relatively prime now gets transferred to this new moduli as well. Note that just like the mk's, we also have this. The n's are also pairwise relatively prime for I not equal to j, and both I and j lie between 1 and r inclusive. Now these things can further be simplified. Why? Oh, and one more thing. Actually, why did we do this? it looks almost like what we previously had. So have we got any advantage at all? Otherwise it will be in vain. No? I mean, what is the need for again getting another system if it just has all the properties of the previous system? Well, the advantage now is that, you see, previously we had this, right? dk is the GCD of AK and MK, and dk is not necessarily 1. Now, however, after dividing these two integers by dk, we are getting this GCD of AK divided by dk and MK divided by dk. From a result about GCDs, if you go back there, you will see that when you do this, when you divide the given integers by the greatest common divisor, then they do not have any common divisor left between them except 1. And that is why the GCD becomes 1. In other words, this is what AK prime and this is what NK. So now in this new system of congruences, here also we have such GCDs. They all are equal to 1. So that is the simplification. So let us just simply note this. In fact, this is for our own understanding. We will simply write like this. Note that the GCD of AK prime and NK is equal to 1 for all the possible k's. And that is why now the equations that, the congruences that we are looking at, each one is solvable, just like the previous system of congruences. There also we had solvable congruences. But because the GCD is 1, each one will have a unique solution, modulo the corresponding modulus. And additionally, because of this thing, now these congruences can be further simplified. How? You see, you remember that the GCD of two integers can be expressed as a linear combination of those integers. So let us use that fact to the kth congruence. In fact, let's continue from here. This means, not perhaps write this means because we know what it means, but this implies that, say, AK prime alpha plus NK beta is equal to 1 for some integers alpha and beta. It's enough to keep only one congruence here, right? A general one, so let me simply write the kth one, NK, because I need space. So we are now looking at a general congruence in that second system for some integers alpha and beta. So if you now look at this congruence and look at this relation, what can you possibly do? How can you possibly use this relation here to simplify this congruence? Note that from this relation we get another congruence. Thus, and that congruence is this. Let me write it slightly differently. Let me write alpha first. AK prime is congruent to 1 modulo nk, because if you take the difference of AK prime alpha and 1, that is AK prime alpha minus 1 is equal to minus beta times nk, and that's divisible by nk, and that is why this is congruent to 1. Now we can use this congruence here very nicely. How? What you do, you multiply both sides of this congruence by alpha. Alright, so if you do that, what will you get? Now the general congruence of our second system is going to get transformed into something else. This one will imply alpha AK prime x congruent to alpha BK prime. Mod nk of course remains mod nk. Now alpha AK prime is congruent to 1, and that is why alpha AK prime times x is congruent to x. So you can write x here. If this certainly looks a little bit confusing, you can argue like this. Actually, this is what the argument that lies behind all these things. I mean, whenever we suddenly write something like this now, you should always know that we have skipped steps, and those missing steps are this. From this congruence, what do we get? We get alpha AK prime x is congruent to x modulo nk, because you can multiply both sides by the integer x. X no doubt is a variable, but after all it's an integer, right? An unknown integer. So now this is congruent to this, and this is also congruent to x. So x should be congruent to this, because congruence is a transitive relation. It's symmetric, it's an equivalence relation. And that's what the missing step is here. And that's how we have got this. And that's why every congruence of the second system further gets simplified into a congruence which looks like this, which is simply x is congruent to some integer mod nk. And that's how we get a third system of congruences, where the congruences are going to look like this. X is congruent to some C1 modulo N1. These N's, however, do not change. From the first system, when we came to the second system, there the MKs changed to NK. But now the N's remain N. X is congruent to CR mod NR, where that condition also remains, that the moduli are pairwise relatively prime or pairwise coprime. That means it's enough to consider only this type of system. Now, if you have only one congruence here, because no one is saying that you have to have R greater than 1. Even a single congruence is also, in a sense, a system, a very simple system. Then you actually do not have to do anything, because solving, say, the first congruence means what? You already know what the x's are. The x's are those integers that are congruent to C1 modulo N1. So their general form is going to be C1 plus N1 times some other integer. However, the problem is non-trivial because you have not just one congruence but simultaneously many congruences, and the moduli are different. Okay, not just different, in fact pairwise relatively prime. So finding a general X that is going to simultaneously solve all these congruences is still not trivial, and that's what we are going to see next. So let's see what this new problem, where this new problem takes us. This kind of problems were considered long ago by the Chinese mathematicians in the 1st century AD. The Greeks also considered such problems in what is that thing called? I cannot remember these names because these are in Latin. No, Introduction Arithmeticae by the Greek mathematician Nicomachus in 100 AD. Such problems were considered, and the Chinese mathematician Sun Tzu, I don't exactly know how to pronounce it, so I apologize if I am pronouncing it incorrectly. But anyway, he posed such a problem. Find, which is something like this: find an integer which leaves the remainders 2, 3 and 2 when divided by 3, 5 and 7 respectively. That means we have to find an integer which when you divide by 3 it leaves remainder 2, when divided by 5 it leaves remainder 3, and when divided by 7 it again leaves remainder 2. So such problems were considered so long ago, back then. And the Chinese, in fact, they did some pretty nice contribution to this kind of problems, and in their honor, the next result that we are going to see, which involves a solution to such a system of congruences, is called the Chinese Remainder Theorem. So that's the main thing, in fact, today. So let's see what this theorem is about. The theorem you will see is going to consider such a system of congruences. In fact, Sun Tzu's problem itself translates into such a system of congruences, if you think about it. Directly you can write 3 congruences for that problem. But anyway, let's now see our theorem 4.8. Chinese Remainder Theorem. And the theorem statement is simply this: let n1, n2 and so on, nr be positive integers that are pairwise relatively prime, i.e. GCD of Ni and Nj is equal to 1 for all possible I and j, but distinct I and j. That's what being pairwise relatively prime means, or pairwise co-prime also you can say. Then This system of congruences has a solution. Here, however, the other integers are ai's, not bi's. You can give them any name. Then x is x congruent to a1 mod n1 or I should perhaps write here then the following congruences have a solution that is unique modulo the integer which is the product of those moduli. Okay, so the system will have a solution and modulo this integer there will be only one solution. Let's now prove this. The proof is really not that difficult, you just have to consider the right things. And in this, obviously, we are going to use our theory of a single linear congruence. Let us start by considering this integer and let's give it a name. Let's call it small n. For this case, let nk, capital Nk, be the integer n divided by nk. In other words, because n is the product of all the nks, in this they all will be there except nk. K minus 1 times k plus 1 n r. All right. For each such k, consider the linear congruence. Nkx congruent to 1 mod small nk. The first question that arises is whether this linear congruence is solvable. Let's see. For solvability, of course, you need to consider the GCD of the coefficient and the modulus. Now, the way we have defined these coefficients, capital Nk, they are relatively prime to the modulus, corresponding modulus. But why? There is a reason. You see, this is how we write. Note that since the small ni's are relatively prime, pairwise relatively prime, we have this equal to 1. Why? You see, that's because there is no common prime factor between Ni and Nj if I and j are different. Fine. Now let's look at these two numbers, capital Nk and small nk. In capital Nk, we have all the ni's except small nk. That means that whatever prime factors that these other ni's may have, that's not available in Nk. And whatever prime factor Nk has will not be available in any of these. And that is coming from here. And that is why there is no common prime factor between these two numbers as well. And that is why their GCD is 1. But 1 of course divides this number 1, and that's why this congruence has a solution and actually also a unique solution modulo Nk from our theory of a single congruence, linear congruence. So let's just give it some symbol, some number or something, say star. So the congruence star has a solution. Let's just call that solution xk. Okay. Actually, you know that when we say a solution, truly there are infinitely many integers that you can put in place of x. But modulo nk, there is only 1 because all these integers are going to be congruent to one another modulo nk. So, and we have assumed to not consider them to be different. You remember that. So essentially there is only one solution. And in fact, among all such integers, you are just choosing one of them and calling it xk. Now, consider the following integer. With the help of these solutions nk, we are now going to write an integer that will involve everything, all the small nks, xks, everything. Like this. Capital N is equal to n1 a1 x1 plus n2 a2 x2 and so on nr ar xr. What property does this capital N have? Is it the sought after solution? Let's try to think of it. Choose any k in this range. We will now try to see if this capital N will satisfy our original congruence, which was the kth congruence. And what was that? That was this, x congruent to ak mod small nk. Whether this capital N will solve this. If it solves this, then since k is any k, so it will then solve all the congruences in our system. Is that the case? Note that for a k, this is perhaps not the best way of writing it. We should not perhaps write like this. For a k, we mean a k which is in this range. So you can write it in a better way, but you do understand what I am trying to say. Oh, sorry, not k, not k. I wanted to write something else, j, such that j is not equal to k, we have this nj is congruent to 0 mod nk. Why? Well, that's because what is nj? Nj is the product of all these ni's divided by nj. Because j is not equal to k, so even after dividing, you still have nk here, and so your nj is divisible by nk. That's what we have written in congruence form. Nj is congruent to 0 mod nk. This means that if you start calculating what n is congruent to modulo small nk, those terms that contain these nj's will vanish because of this congruence. In other words, almost everything on the right hand side vanishes except the kth term, right? And what about the kth term itself? What can we say about that? Let us do it in steps so that we don't get confused. So because of these things, we next have this. Hence, n is congruent to everything vanishes except nk, ak, xk mod small nk. However, now you recall this congruence. Our xk is in fact nothing but a solution of this congruence. That's why nk xk is congruent to 1 mod nk, and we can now use this here. Because of this, this part becomes not this part, nk times xk becomes congruent to 1 mod nk, so that ultimately becomes ak. So you see that yes, our n actually satisfies the kth congruence of our original system. Hence, n is a solution, not writing everything properly, okay, just showing the main things. N is a solution of the given system. But we are not done yet. We still have to show that this solution is the unique solution modulo this product, that is our small n. So the next part is that. Suppose say n prime is any solution of the given system of congruences. Then for each k in this range, n is already satisfying this kth congruence, but now n prime will also satisfy. So we get this n prime, or let me first write n. N is congruent to ak, but n prime is also congruent to ak modulo nk. That means they are congruent to each other modulo nk. Although we do not have, once you do not write ak, you just have n and n prime. But still, that modulus is changing, right? This means, because the nks are positive integers, non-zero in fact, that they divide n minus n prime. So all the nks divide n minus n prime. Now combine this with the fact that the nks are pairwise relatively prime and use a previous result. Which result? Corollary 2 to theorem 2.4. Since the n's are pairwise relatively prime, it follows from that result that their product will also divide n minus n prime. Actually, there is a general result, right? Not exactly result, but it follows from the definition itself. Yeah, but before we get somewhere else, let me complete this. It follows from corollary 2 to theorem, what's the number? 2.4, that the product of these n's also divides this difference, i.e. small n divides this difference. So n is congruent to n prime mod n. So modulo this small n, essentially there is only one solution. What I was trying to say back there is that in general you have this, no, say you have, so this is the proof, the proof is complete here. This corollary 2 to theorem 2.4, say you have 2 or maybe 3 integers, right? They are, say, positive integers. For the sake of simplicity, consider positive integers. And suppose that all of them divide something which is also an integer, say capital N, that is A divides N, B divides N, C also divides N. Then by the very definition of LCM of these A, B and C, their LCM also divides M. Now, when these are pairwise co-prime, the LCM becomes their product, and that is why their product divides N. That's what we have in this corollary, and that's why we are getting this. So now we know when such a system of congruences has a solution and what that solution is. So let us now see 2 examples that will illustrate this. The first example is going to be that problem by Sun Tzu. And the second example will be something else. So let's see Tzu's problem first. So what he was asking us was to find an integer that will leave the remainders 2, 3 and 2 when divided by 3, 5 and 7. And that means finding an integer x that is congruent to 2 mod 3, that is also congruent to 3 modulo 5 and again 2 mod 7. These three congruences. So you just follow the proof of the theorem that we did just now. So first of all, you consider the integer small n. So this becomes 105. But I have to keep looking at this because, I make this type of mistakes very easily. With numerical values, I always make mistakes. This is my weakness. And then you then have those n's. N1 will be this n divided by 3. That means in this product you do not consider 3. So 5 times 7 is 35. N2 will be 3 times 7, 21. And N3 will be 3 times 5, 15. So the next thing you will consider will be those congruences that will involve these capital N's. That means you next have to consider 35x congruent to 1. Yeah, perhaps I should write these congruences like that, as an equation array there on that side. (35x) is congruent to 1 modulo 3. Next, 21x congruent to 1 mod 5 and 15x congruent to 1 mod 7. And one can solve these congruences, following the usual procedure of solving single linear congruences. Either you use that, you can of course see that the GCDs of these coefficients and the corresponding modulus are all equal to 1. That's how the setup is. So you express the GCD of 35 and 3, which is 1, as a linear combination of 3 and 35, and that way you will get x, or you can just simply find these solutions by inspection. Anything you can do, and it turns out that you have these solutions. These are not, of course, unique solutions. Unique from modulus perspective, they are unique, but for individual integers, you can have other integers as well. The simplest ones are, I think, given here. So x1, which is a solution to the first congruence, is 2. And for the second and third one, you can take both of them to be 1. And that's why what will be your capital N? Capital N, let me first write the thing what it is. N1, A1, X1 plus N2, A2, X2 plus N3, A3, X3. So N1 is 35, A1 is 2 and X1 is 2. plus N2 is 21, A2 is 3 and X2 is 1 plus 15 times 2 times 1, and this one turns out to be 233. But again, let me see if I have made any mistake. 35, 2, 2, 321, 1, 215, 1, okay. And that's why this is a solution. Now you can of course simplify this solution, because it's going to be modulo 105. If you put x equal to 233 in the original congruences, each one of them will be solved, but you can put something smaller also. We have the solution x congruent to 233, and that turns out to be congruent to 23 mod 105. So instead of 233 you can take 23 also in place of x. Now next let's see another. Here however we won't initially have a system of congruences but only one congruence. And that congruence is going to be this. 17x is congruent to 9 modulo 276. Now we are going to first of all factorize the modulus. If one factorizes 276, one sees that one gets 3 primes. 3 primes means we do not actually simply get primes, but we do get this 3 times 4 times 23. 3 and 23 are prime. 4 itself is not prime, but 3, 4 and 23, these integers are pairwise coprime. That's what we need. So instead of considering this single congruence, we can also consider these 3 simultaneous congruences, where this part does not change. 9 here, sorry. This part stays the same in the 3 congruences, but the modulus changes. You have to, however, carefully see if the logic is okay. Is it okay to solve these 3 congruences in place of this single one? If so, why? You see, any x that satisfies this is automatically going to satisfy this also. Why? Say you have an x that satisfies this congruence. What does that mean? It means that 276 divides 17x minus 9. That's what it simply means. But that automatically means that 3 also divides 17x minus 9. Why? Because 3 divides 276. That's why. Similarly, the other congruences will also be satisfied by that x. Can we go back? I mean, if we find a solution to these congruences, will that also solve this congruence? Yes. Why? Because if you find such an x, then 17x minus 9 will be divisible simultaneously by 3, 4 and 23. But then you can use that corollary 2 theorem 2, 4 and combine the moduli to conclude that 17x minus 9 is also divisible by 276. That's why whether you solve this one or you solve this system, they are the same thing. Now here the way this system has been solved is slightly different. Different means we are first of all going to see something which will immediately simplify the matter. You can see that 9 is already divisible by 3, and that's why in place of 9 you can simply write 0. So the first congruence reduces to this. In a similar manner, what about the second congruence? Because 9 is congruent to 1 modulo 4, so you can write 1 here. And the third one unfortunately has to stay just like that, because you cannot actually do anything useful to it. Then can we go further beyond this? Yes, you can change this one. This one reduces to this one. Why? Because if you think in terms of divisibility, it just simply says that 17x is divisible by 3. 17 anyway is not divisible by 3, and 3 is a prime, so 3 has to divide x, and that just means this. This one, however, it can also be simplified. But how? It ultimately simplifies to this. X is congruent to 1 modulo, I wrote 9, 4. X is congruent to 1 modulo, that's why I got confused a little bit. See, that's how mistakes happen. The way you can solve this, simplify the second one and get this one, is that 17 is congruent to 1 modulo 4, because 4 times 4 is 16, 16 plus 1 is 17. So that 17 x actually is congruent to x mod 4. So in place of 17x you can just simply write x. Now in this somewhat simplified form, things have become particularly simple. So simple that we can start with this congruence. What does this say? It says that x has to be divisible by 3. So the general form of x is going to be like this. It's some multiple of 3, where k is an integer. K belongs to the set of integers. Now you put that 3k here in the second congruence, you get this. 3k is congruent to 4, right? However, if you look carefully, you can add k to both sides. If you do so, on the left hand side you will have 4k, on the right hand side you will have k plus 1 mod 4, and the left hand side now becomes 0. So we are going to get 0 congruent to k plus 1 mod 4. Now if we switch places a little bit, we get this same thing, because congruence is a symmetric relation, and this one implies this. But minus 1 is congruent to 3 mod 4. If you want, you can keep minus 1 also, but for some reason we tend to go towards positive values. So K now has to be of the form 3 mod 4, and that's why K looks like this, 3 plus 4 times what variable J, okay. You can write anything here, but I want to write it exactly like how it is in the book, where J is some integer. So now you know how X looks with this new information. So X is now of the form 3 times 3 plus 4J, or 9 plus 12J, where J is any integer. And now you put that X here. Okay. Doing that, you are going to get 17 times in the third congruence 9 plus 12J congruent to 9 mod 23. This one is a little big, but it will also be simplified. It turns out that a direct multiplication and doing whatever needs to be done leads to this. 204 J is congruent to minus 144 mod 23, and that thing, if one simply sees what these numbers are congruent to, modulo 23, leads to 20J minus 6 mod 23. Now if you add 3J to both sides, this side will become 23J and that side will become 3J minus 6 mod 23. So you get 0 congruent to 3J minus 6 mod 23, or 3J is congruent to 6 mod 23, or J is congruent to 2 mod 23. Do you see how we are able to suddenly cancel 3 from both sides? That is because 3 is relatively prime to the modulus. Otherwise, you will have to change the modulus by dividing by 3. But anyway, now we have got J congruent to 2 mod 23. And from this, we get a structure of J, how J generally looks. So J is going to look like this. J is equal to 2 plus 23T, where T is any integer. Now use this value there. Here, X is now going to look like this, 9 plus 12 times 2 plus 23T. So ultimately what will it be? It's going to be 33 plus 276T. These are all the solutions, and T can be any integer. All the solutions to that original congruence, that single congruence. And one of those solutions you get by taking T equal to 0, which is 33. You can go back to those congruences, the first original one and the 3 ones that we derived from that. In all of them you put 33, you will see that yes, it satisfies. In fact, you can put this general value also, then also you will see that all these values satisfy all those congruences. So that's how we have this. But the section is not over here itself. After this, we have a brief discussion on linear congruences in two variables. So far we have been considering only one variable, but next there is that consideration also. That, however, I won't discuss today. So we'll do it the next number theory video. And after this we have our next video next Saturday. So see you then. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.